Hi everyone. It's so wonderful to see all of you here today. Thank you so much for joining us here in Vanadzor. So my name is Nora and I work as a data scientist at a fintech startup called Stratyfy. It's based in New York City. What we do at Stratyfy is mainly the company is operating in an interpretable AI field. And today as well, I'm going to focus on transparent machine learning and fair decisions in algorithms, and I will also go through a few techniques to add a transparent layer on our black box ML models. Basically, we will explore why we actually need transparency when building models. Then we'll go through a few interpretable models that are explainable by design. And of course, in the end, we will go deeper into a couple of techniques that can be used to explain the predictions of our black box ML models. So before going deep into why we actually need transparency, a little bit of background of the company that I work at. At Stratyfy, we provide predictive analytics solutions to financial institutions and insurance companies. But the crown jewel of ours is our proprietary algorithm, which is based on probabilistic logic, and it combines human expertise with statistical learning. And by doing so, we enable the users to have the accuracy of most of the machine learning models, whereas the algorithm itself is interpretable by design. So, okay, why do we need transparency when building our predictive models? One of the main reasons is when I build a model, I want to be able to trust the model results. I want to see how the model is making predictions, and I want to track the path to those predictions and decisions. For instance, when I apply for a loan at a bank, and the bank is using some kind of a modeling approach to decide whether to extend a loan to me or not. And for some reason, they decided not to do that. And then I want to know the reason behind that decision. And I want the bank to provide me some explanations. On top of that, which is more important, there are industries which are very highly regulated, especially in the US, and I think it's becoming more of a standard worldwide. And one of those industries is finance. And the governments, they impose those regulations on those industries so that those financial institutions make non-discriminatory decisions, so that those decisions are fair. And last but not least, when I have an interpretable model, I can see what's going on inside my model. And if the model is performing in an unfair manner, I can easily intervene and I can correct for those unfair and biased decisions. In fact, this bias in algorithms has grabbed a lot of attention during the past decade, and is becoming more and more important for us to closely monitor our models and how they perform, and to make sure that they are not discriminating against different genders, races, and etc. And if they do, it can lead to very scary outcomes, and it can affect human lives. And actually, in the past, there were cases where this happened, and the algorithms made unfair decisions. And one of those cases is Apple Card. So I think it was in August of the last year, Apple issued their card, and there was a huge scandal which started from Twitter, because one of their users, he tweeted that he and his wife applied for this card, and he got 20 times more card limit than his wife. In the case where they shared the same household and his wife had a higher credit score. And on top of that, Goldman Sachs, which was the issuing bank of the card, one of their explanations was, okay, our model didn't look at gender, so we can ensure that the model is unbiased. And this is the first intuition when we deal with bias in algorithms. We're like, okay, if I don't include the protected variable in my model, then it should be unbiased. But it turns out it's not the case because those protected variables can be highly correlated with some other variables that we use in our models. So in that case, we cannot ensure that the model is unbiased. So for instance, race and zip codes, they are highly correlated. And even if I do not take race into my model, but I take zip code, then already I cannot ensure that I have a fair model. And just another example is Amazon. So it was quite some time ago. So they came up with this completely automated, powerful recruitment system. And the system actually was reinforcing the bias that was in the data. And it was discriminating against women based on their resumes. So now we kind of understand why transparency is very important and why it is crucial to have this transparency when building models. And in fact, there are a lot of interpretable models that are explainable by design. And here I just chose a few of them: logistic regression, decision trees, decision rules. I won't really go deep into each one of them. But the main limitation that they have is they are really good at explaining, but they do not have very high predictive power. So we can place them in this upper left part of this graph, where we have high transparency but low accuracy. And then on the other extreme, we have neural nets, boosted trees, like XGBoost or gradient boost, which have very high accuracy, but they lack transparency. And as you can see, the sweet spot on the graph is this green square, and we would like all our algorithms to be there. And so far, to date, probably this probabilistic logic is the best candidate to be placed there, because it combines human knowledge with machine learning, and by doing so, we are getting both high transparency and high accuracy. But there are some techniques which can be used to make a little bit our black box ML models transparent and to move them to this green square. And next I'm going to just talk about those techniques. So we see that those interpretable models are not great at predicting. So what if we still want to use our black box ML model, but we want to be able to explain the predictions that the model makes? There are a few techniques to do that, and here I just chose two: LIME and SHAP values. So what is LIME? It's local, interpretable, model agnostic explanations. How it works: we have our black box model, we have our data. Here as an example, it's financial data. And we train the model on the data and make predictions. So at that stage, we already have all the components to be able to use LIME. What we do, we take one individual prediction out of all the sample, and this is the key thing about LIME, that it's local. So we explain one single prediction at a time. And what we do, we take that point of interest, and then we select a vicinity around that point of interest. And what LIME does, it just generates cases, random cases from that vicinity, and just does sensitivity analysis to explain that exact prediction. And here, on this right part of the slide, you can see the output of LIME if we would implement it in Python. And it's very easy and straightforward to do it in Python. But what we can see here and how we can read it is that, for instance, income of this person was quite low. And that's why it dragged down the probability of this person repaying the loan. And this is one of the reasons that the bank decided not to extend a loan to this person. And we can just explain the same way all the other variables. And this is a very powerful approach, because in this way, we can just decompose the whole black box model into explainable contributions of each variable to the final prediction. So Lime works quite well. It works really well in most of the applications, but it has some limitations. And one of the limitations is that it's local. It provides local explanations. So when we extend it to global picture, we may get very unstable results. And actually what we did at Stratyfy, we conducted an experiment. We generated data, and then we used XGBoost to train and make predictions on the data. And then we used Lime to explain those predictions. And what we saw was that for two similar cases, and we had just two features, X and Y, and we saw that for two similar cases, we were getting completely different explanations. And they were actually affecting the prediction in opposite directions. So for instance, that would mean, following the last slide, that income for one person would affect positively to the repayment of the loan, and for the other person, the same income would affect negatively. So that means already the global picture is not consistent. And a few other limitations is that, for instance, it's very dependent on hyperparameters that we choose when building a model. And also it's dependent on the size of the vicinity, basically the neighborhood that we choose from which Lime is going to generate cases. And the next technique is sharp values. The output of sharp values is quite similar to Lime. However, the mathematical definition is different. And sharp values are based on cooperative game theory. How does that work? So here I just have an illustration of a famous Russian fairy tale about this huge turnip, and all the family members, they want to pull out the turnip of the ground. So how can we attribute each family member's contribution to this whole process of pulling? What we can do is we can compute the marginal contributions of each family member, then we can permute the order how they approach the turnip, and then we compute the marginal contributions again. Then in the end we can just average out all the contributions over the whole list of permutations. So this is again very, very useful and very powerful method to use when we want to explain how much each variable contributes to the final prediction of our black box models. But again, for sharp values as well, we have limitations, and with Lime, they share quite some limitations, because they are really great at explaining locally, so they work very well. But when we expand it to global explanations, and we can do it because it's additive, then we may get inconsistent feature importances picture. And another thing is that even if I change the seed when building my model, then the feature importances may change. And the final point about sharp is that model developers, they can manipulate the explanations provided by sharp, and they can hide biases intentionally. And this leads me to the last point of my presentation. So transparency and fair decisions are very important and crucial topic. However, there are some examples, there are some facts that I want to give you to be careful about when using transparency. The first example is when it's basically followed from the last slide, is when developers, they can just manipulate those explanations that that the transparency can provide. So one of those examples is that, for instance, when I buy something on Amazon, there is this message. You may be interested in some other products because some other people similar to you, they bought it. So they provide explanation, but I don't know how much I can trust that. Because in the end, what Amazon wants is me purchasing the product. So be mindful of that as well. Another example to be careful when using transparency is that there is no unique definition of bias. There is no unique metric that we can measure the bias for. So people came up with different metrics and all of them are valid, but it turns out that a single model cannot be compliant with all the bias metrics. And the fun thing is that one model can be compliant with one metric, but then it can be discriminating against both classes according to other metrics. So this is also something that needs to a lot of research, and we need to bear this in mind as well. And just finally, transparency is a really powerful technique when we use it in a fair manner. And I think if we continue pursuing the research in transparent AI, in the future we will be able to create more intelligent machines. And this leads me to the final point of thank you, and please reach out if you have any questions or if you want to know more. And I think I had some sources here, but for some reason those sources are not visible on the slide. But I will ask the organizers to just share the whole presentation. You can see a few sources about the articles that we wrote at our company about bias and transparency, and also the links to the libraries that can be used for shop and line. Thank you.